So this is in second year. So from what I've observed, from two topics, rather three, most of the questions are asked. So first one is binding energy, and second one radioactivity, and third one fission, nuclear reactors, and some theoretical questions could be asked from fusion too. Right. But most of the questions are from these three. There are other minor things. So for example, at the starting, when we introduce two different types of nuclei, we discuss isotopes, isotones, isobars, etc., etc. We have isomers, isodiaphers, etc. We have this kind of different nuclei where we can arrange them depending on the A and Z properties. So usually a nuclei is denoted by, for example, X is a radioactive nuclei, or it could be stable too. Usual notation is Z and A, where Z is atomic number and A is mass number. Usually Z atomic number denotes number of protons. This is the characteristic property of element, right? Not number of electrons, because electrons, an element can either gain or lose provided sufficient energy, right? We call it first ionization energy, second, and so on. But protons, they remain same. Well, we can change the number of protons too, depending upon the kind of energy that we give, but that kind of falls under nuclear reactions. But usually in the normal conditions, Z won't change. So Z is the characteristic property of a given element, and A is the mass number, which is the sum of protons and neutrons, right? So on this A can vary, right? And so number of neutrons we can obtain from A minus Z. So A minus Z is number of neutrons, and so based on these things we define these things: isotopes, isobars, isotones, isomers, isodiaphers, etc. So same A, same Z, same A minus Z. Well, there is on one more property. X is, for example, Z is my number of protons and A minus Z is my number of neutrons. What is the excess number of neutrons that I have? So A minus Z, number of neutrons minus number of protons, right? This gives us what is my excess of neutrons compared to protons, right? So this is this much, so and that is A minus 2Z. So based on this also we call we just categorize the given pair or whatever number of nuclides into these things, right? So usually even A and even Z, they're the most stable. This we kind of say from shell model, right, which usually discussed in later classes. But shell model is essentially kind of an electronic configuration except for nucleons. not electrons. Rather, I should call it nucleonic configuration, right, if you will. So how nucleons get arranged, just like how electrons. So here we have some rules, like half Pauli exclusion, etc., and one more. Yeah. So just like that, we have nucleonic. There are some rules, right? Depends on its multiplicity, depends on its spin, etc. We arrange these nucleons also inside a nucleus. So based on those things, based on not only that, based on experimental observations also, we can say even A and even Z are more stable, right? And yeah. So now if I come to binding energy, so this binding energy, well, so let's take helium, right? Just an example, 2 and 4. So 2 protons and 2 neutrons, right? So these are nucleons, by means they reside inside the nucleus, and electrons, we know, they revolve around the nucleus. So these nucleons, something has to hold them together, right? And we call that usually strong nuclear force. And besides this force, what how do they bind together is that, so if I take one neutron, right, it has some mass, and since these are subatomic particles, they have very small mass, and uh, we can represent them in normal units like kilograms, but it would be very less. And we do know mass of electron is in normal terms 9.31, around 10 to the power of minus 31 kilograms, and proton is around 1836 times heavier than electron. And these are kind of very small numbers to have an estimate, right, uh, to make them comparable to each other. We choose another system of unit, that is AMU, that is called atomic mass unit, right? And 1 AMU is usually defined as 1/12 of 1 C12 atom, right? And this comes out to be around 1.66 into 10 to the power of minus 27 kilograms, right? So usually nucleon, right, it's measured in AMU to get relative, right, to scale it to 1. For example, neutron has an atomic mass unit of something around 0.009 AMU, well, almost 1, right? So you get the point. So usually we measure these nucleon mass in terms of AMU. So as I said, this contains 2 protons and 2 neutrons, right? So if I join all this, I should get this nucleus, right? And well, it's not that easy, but I'm just telling in terms of weight, right? So if I take in terms of mass, so if I take 2 protons mass, so that is 2 into mass of protons plus 2 into mass of neutrons. So I should get the total amount of mass, this mass. At the same time, from the spectroscopic studies, we can find out what is the exact mass of this nucleus, and this turns out to be some mass of some nucleus, right? So what we have found is, so individually this constituent mass is bigger, than whatever spectroscopic studies which we have found experimentally, right? So this is greater than this, so some mass is kind of disappearing, that mass is actually converting into energy, and we call that mass energy equivalence. So that means the given mass can be converted into energy and vice versa, energy can be uh, converted into mass, well, which is kind of uh, the whole thing said by Einstein. And so this, whatever we call this difference in mass, that we call it as mass defect, delta m, right? And equivalently this can be converted into energy, and this much of energy is used to bind all these constituent nucleons, and we call this energy as, since this energy is used to bind these nucleons, right, this energy is called binding energy. So conversely also, if I provide this much amount of energy from outside and project it exactly to the given amount of nucleus, I can split them into constituent nucleus, because I am providing energy, and that in turn is used to create the individual masses. So energy is kind of being converted back into mass. So yeah, energy and mass are interchangeable given the right conditions and the right scenario, the reactions, right? So anyways, this is mass defect and this is binding energy, the amount of energy is required, or the amount of energy which is kind of made by converting the mass to bind the individual nucleons together, right? That energy we call it as binding energy. And another important term or important thing which we consider is per nucleon, this binding energy per nucleon, meaning, for example, the total number of nucleons here is 4, so divided by 4 here for this particular nuclide which we took. So this is also an important one which tells us about a given nucleus, right? Usually there is a graph for this too, and that kind of goes like so. If this is atomic mass here, I'm taking in x-axis, and in y-axis I'm taking this binding energy per nucleon. So for smaller atomic numbers, or rather atomic masses, let's say up to 30, it's kind of less, but as we said, even A and even Z are stable, so for those kind of nucleus usually it gets high and then low, and then it gets kind of peaks. These peaks represent kind of stable, very stable nuclides, and then from 30 you'll get one sharp peak around here, and then almost kind of plateaus, and then goes something like this. Well, this is not exactly correct, but the idea is essentially the same. So from 30 to around 170, the binding energy per nucleon almost stays constant, which kind of tells us that binding energy per nucleon is independent of A from 30 to 170, and for iron it's highest, And as I said, smaller ones, these are kind of very stable. You could say noble gases, helium, neon, etc., etc. And so usually the lighter elements, if you fuse, uh, they kind of gives us higher energy, right? So they provide elements which has more binding energy per nucleon. So lighter elements tend to fuse, and higher elements tend to diffuse, which is called fission, and which provides daughter nuclei which are more stable. Could be unstable again. We'll get into radioactivity that bit, but usually from 30 to 70, sorry, 170 binding energy per nucleon tends to be constant. And which kind of tells us something about nuclear forces. And nuclear force properties also are kind of important. They could ask questions from this. And nuclear force is actually short range, and it is strongest in terms of intensity and short range. And another peculiar one, it is both repulsive and attractive. Repulsive when the nucleons come very close together, less than 0.5 Fermi, femtometer of Fermi, and attractive around from 0.5 to around 3 Fermi. Above 3 Fermi, well, flat lines, no nuclear force. Right. This is to prevent the collapse, the self-collapse of matter, which we kind of got it. And attractive, yes, this is what usually makes the nucleons come together, well, once they fuse, right, from binding energy. And it is the strongest, and it is independent of charge. So between a proton and proton, proton and neutron, and neutron and neutron stays the same, independent of charge. And it is not a central force. It does not act along the line joining the two nucleons or inverse square dependence. It's something else. It is an exchange force actually. There is some other particle exchange part, kind of force which you'll study later. Now this binding energy, I think we've got an idea, right? Well, the formula. So the formula is, again, energy is mc squared, so mass defect into c squared. Not relativistic, by the way, this is stationary. And so delta m z into mp plus, and this is a minus z number of neutrons into mass of neutrons. This is our mass defect, well, minus given nucleus into c squared. So if I usually measure it in kilograms, right, usually given in AMUs and all, and this could be written, right, if I convert the whole thing into MeV, which is the kind of normal conventional unit which we use in nuclear physics, we get, so we multiply this whole thing ZMP plus A minus Z into Mn, which is my constituent nucleus matter, and given nucleate mass into 931.5 MeV. Right. So this is how we calculate binding energy. And so when a reaction occurs, right, for example, X is Z plus Y is Z gives rise to some Z is Z plus some constituents, could be neutrons, could be alphas, could be betas and all. Well, let's say some other some X dash is it, right? So when this reaction occurs, could be exothermic and endothermic. If it is exothermic, it releases some energy Q, right? And this Q, well, some energy gets released if it's exothermic, and that we call it as Q value of the nuclear reaction. So this is exothermic reaction, and this is the Q value. Q value is the total amount of energy released, and this energy is usually distributed among products, right? Usually in terms of kinetic energy, meaning they fly off in different directions. And so kinetic energy, and if they encounter any other medium or anything, so usually this kinetic energy in turn converts into heat, could be light, could be sound, etc., for the given chemical reaction. But if I consider particularly nuclear reaction, right, there are no kind of light or anything, rather mostly kinetic energy. For example, I'm considering fission. So the daughter, which we call the reactants usually daughter products for in radioactivity, by the way, which fission is kind of nuclear, but not radioactive. It is a nuclear reaction. So anyways, the products kind of takes that energy and they kind of fly off in different direction. So since these reactions are, there are no external forces, only internal forces are present, right, we can apply LCLM, law of conservation of linear momentum. We can apply this to any reaction because all reactions are kind of internal electromagnetic interactions or nuclear interactions. So since all are internal, we can apply this conservation law, which is kind of universal to every nuclear reaction there is. So LCLM we can apply, right? If I'm not mistaken, if there is some exception to this, probably there is some, but for most of the cases, right, and for as far as we consider this 12th standard examination procedures, LCLM we can apply. So yeah, so if I apply that, for example,